friends, welcome to the presentation on Taylor's and Maclaurins theorem. I am Dr.Rajeshree. In our today's presentation, we'll see Taylor's theorem with Lagrange's form of remainder and Maclaurin's theorem with Lagrange's form of remainder. So friends, we'll see both these theorems one by one. Firstly, Taylor's theorem with Lagrange's form of remainder. Statement: let f be a function defined on close a comma a plus h such that fn minus 1 is continuous in close a comma a plus h. Fn exists in open a comma a plus h, then there exists a real number theta lying between 0 to 1 such that f of a plus h is equals to f of a plus h into f dash a plus s square upon 2 factorial f double dash a, so on, h raised to n minus 1 upon n minus 1 factorial fn minus 1 a plus h raised to n upon n factorial fn a plus theta h. Here, h raised to n upon n factorial fn a plus theta h is equals to Rn is called Lagrange's form of remainder after n terms. Replacing a plus h is equals to x and h is equals to x minus a, we get another form of Taylor's theorem with Lagrange's form of remainder. Let f be a real valued function defined on close a comma x such that fn minus 1 is continuous on close a comma x. Fn exists in open a comma x, then there exists a real number theta lying between 0 to 1 such that f of x is equals to f of a plus x minus a into f dash a plus x minus a square upon 2 factorial f double dash a, so on, x minus a raised to n minus 1 upon n minus 1 factorial fn minus 1 a plus x minus a raised to n upon n factorial fn a plus theta h. Here, Rn is equals to x minus a raised to n upon n factorial fn a plus theta h is called Lagrange's form of remainder after n terms. Nextly, we'll see Maclaurin's theorem with Lagrange's form of remainder. It is a special case of Taylor's theorem obtained by replacing a by 0. Statement is let f be a real valued function defined on close 0 comma x such that fn minus 1 is continuous on close 0 comma x. Fn exists on open 0 comma x, then there exists theta lying between 0 to 1 such that f of x is equals to f of 0 plus x into f dash 0 plus x square upon 2 factorial into f double dash 0, so on, x raised to n minus 1 upon n minus 1 factorial fn minus 1 0 plus x raised to n upon n factorial fn theta x. Here Rn is equals to x raised to n upon n factorial fn theta x. This is called Lagrange's form of remainder after n terms. Now we'll see Maclaurin's series of some elementary functions. So firstly we'll see expansion of the function e raised to x for every x. Friends, here f of x is e raised to x. You know that all the derivatives of this function is again e raised to x. So f dash of x is e raised to x, f dash of x is e raised to x, f double dash of x is e raised to x, and fn x is again e raised to x. So thus f of 0, if we substitute x is equals to 0, we get f of 0 is e raised to 0 is 1, and even if we'll substitute for fn 0, it is again e raised to 0 is 1. So here the function value and the values of the derivative at point 0 all are same, which are nothing but 1. So substituting all these values in f of x is equals to f of 0 plus x into f dash 0 up to x raised to n upon n factorial fn 0, we'll get here e raised to x is equals to 1 plus 1 into x plus up to x raised to n upon n factorial. So here in fact we'll get the infinite series, that is expansion of e raised to x is equals to summation n equal to 0 to infinity x raised to n upon